Hello, this is the second video in my new series on mechanics. In the first video we looked at velocity time graphs, we looked at the concept of acceleration, and we saw that there were periods where we had constant acceleration. So what is acceleration again? Well, we can get the acceleration from the gradient of this velocity time graph, because acceleration is the rate of change of velocity. And if we unpack that a bit, that's change of velocity. That's probably straightforward. But what does rate mean? It means per second, or per period of time. Yeah. So if it's changing quicker, our rate's high. If it's changing more slowly, accelerating more slowly, then our rate of change is lower, isn't it? So looking at our graph here, we can see we've got three separate periods of constant acceleration. So we've got this first section here. We started off at speed, so velocity was 0. We accelerated at 1 meter per second squared during this till we got to that point there. So what does that mean, 1 meter per second squared? Well, it means that after 10 seconds, we'd be doing 10 meters a second. So during this first phase, we've got a constant acceleration of 1 meter per second. During the second part of our journey, we're steady state, we're just traveling along. So our acceleration during this period is 0 meters per second. We're getting no change. Yeah? So again, that is a period of constant acceleration. It's just the acceleration is 0. And then in the final part, we slowed down and stopped. And here our constant acceleration was -2. We can see that our gradient is negative here, yeah, and we went from 10 meters per second to 0 in a 5 second period, yeah. So -10 over 2, so over 5 is -2. So here we can see that we can construct a journey out of 3 separate periods of 1, 2, and 3 of constant acceleration. It's just the acceleration is different in each period. So let's now have a look at what the maths looks like for one of those periods of time, and therefore how we can use it. Okay, so this is a single period of constant acceleration. How do I know it's constant acceleration? Well, we've got a straight line here in our velocity time graph. Yeah, the gradient is constant through this period of time. Yeah, we've got a constant gradient, and we're going to use certain symbols or letters to represent particular values in our world of constant acceleration. First one is that our initial velocity is always u, our final velocity is v, our period of time is that we're working in is t, and the acceleration in the period is a. Yeah, so we're going to start seeing these letters turning up a lot. So what can we work out from if we define everything that way? Well, the first thing we might want to look at is the gradient of this line and how all our letters stick together. So over the period of time t, we accelerated by I increased our velocity by v minus u, didn't we? And therefore our gradient is going to be v minus u over t. That's our gradient, and we know that our gradient is a. So we've quite quickly created our first formula here, that a equals v minus u over t. But we don't usually write it that way because we probably often know what a is. And we're probably more interested in finding what our final velocity is if we know what our starting velocity is. So it's usually written in this form here, that v equals u plus at, i.e. our final velocity is our initial velocity plus an additional component, which is our acceleration times time. There we go, v equals u plus at. Now, our second formula comes, we want to start looking at what our displacement, our distance is that we're going to be traveling, and we call that displacement, and we call that s. Okay, now if I wanted to know what that was, I could think about the fact that on average here, if I've started off at velocity u and I've ended at velocity v, well, my average velocity is u plus v over 2, isn't it? That's my average. And if I was just traveling at that average the whole time, t, then the distance I would travel would be my average velocity times my time, and therefore here we are, it's going to be s equals u plus v over 2 times t. There we go, which you might think of in a different way, because we can see that that's actually using a trapezium rule as the area under the curve. Okay, so using our two basic formulae that we just created, v equals u plus at and s equals u plus v over 2 times t, we can create some other formulae, and they're all based on how we might use them in practice. So what if I don't know what my final velocity is? How could I find out things? What if I didn't know what my initial velocity is? What if I didn't know what my time period was? How could I find other values that I wanted to find? Okay, so what we're going to do is just rearrange these equations. Here we go. So the first thing is, what if I don't know what my final velocity is? And I might still want to find out what the distance travelled is. Okay, so here's my formula for distance travelled, s. So just distance, yeah, displacement, sorry, I should be saying really. And what's my other formula? Well, v equals u plus at. So I could just substitute that formula into my s formula. And we can see here quickly, can't we, that I've got two terms with u in. They're both multiplied by t. So I've got two u's there. Divide by u. And we're in business. So here we go, ut. That will give us our ut term. Here I've got an at multiplied by t divided by 2. So I get second term, which is a half at squared. So here I can find what my value of s is for my initial velocity, the time, and the acceleration. I don't need to know what my final velocity is. Similarly, and less used, is what if I didn't know my initial velocity but I knew my final velocity? Well, my s formula is still the same. I could rearrange my v equals u plus at to get u as the subject, so that's going to be equal to v minus at, and I could substitute that into my s formula, and when I tidy up I've got s equals vt minus a half at squared. The distance is going to be slightly less. There we go. And the final version, which is actually quite useful, is what if I don't know the time it's taking to do something, but I might know the distance. So here's my s formula. And if I take my v equals u plus at formula and rearrange it to make t the subject, so t equals v minus u over a, I could substitute that into my s formula. There we go. So I've now got on the top u plus v times v minus u. Some of you will recognise classic identity, that's going to be v squared minus u squared. And on the bottom we've got divide by 2a. Now, quite often we don't use it in that form. We want to find our final velocity. So if we rearrange that equation, we would have v squared equals u squared plus 2as. Now that one's actually quite useful, particularly if you were doing like how much does your car slow down. If you know your initial velocity is u, you know what your rate of deceleration is, and you're interested in what speed you're doing, say after 100 meters, you can find your velocity there. So there you have it. These equations are called the Suvat equations. That's an acronym, as you can see, because we use all the letters S, U, V, A and T. And we've derived 5 formulae for working in a period of constant acceleration. And I'm going to leave it at that for now, with that on the screen for you to use. And we'll come back and look at how we use them in practice in the next video.